Yeah, so welcome to Mechatronic systems modeling. This is the first lab, so I will just give a basic introduction to the module, right? So I think you all have covered like 3 or 4 lectures up now, right? So you have done LTI systems. Is that all? It's all right. Okay, so basically, you might be wondering what this module is, right? So I think Professor Migara might have given like an explanation. So I will just sum that up once again. So basically, under control systems, you like talk about a lot of things, right? So basically, I think you all talk about under control systems. You all discuss about basic systems like mechanical systems, fluid systems, thermal systems, electrical systems. So these are like the systems that you cover under controls, right? But there are other systems as well, like chemical systems and biological systems, right? So there are like certain systems as such, right? So if you want to like understand how the systems function, and if you want to like figure out how certain inputs change the output response of the system, or how certain system parameters change the system's overall output based on some certain input, we do that in control systems, right? So we just model the system mathematically, and then you do some sort of like variations to the input and try to obtain the output. So in nature, we don't like very unstable systems, right? We like stable systems. So if you take a basic system like a spring mass damp or your suspension, right? Or in your vehicle. So you actually prefer to not have like a lot of oscillations, and like if you like go over a pothole or a bump, and if you like feel the vibration in your body, then that's uncomfortable, right? And and if you like go over a bounce and like you keep on oscillating the bike keeps on oscillating for like 5-6 seconds, that's also uncomfortable and can like cause some sort of like hardness for the biker to balance the bicycle. So all these things, like these are like responses, right? So if you so I'm just assuming here that you all remember certain factors in control systems, right? Some system responses. So if you take a bicycle and if you like go over, so let's say like you have a bicycle, right? And so basically you have the damper and you have the spring, right? So start this. So say you have like a mass and you have the damper and you have a spring, right? So this is like a recap to what you all have learned all this time, okay? So say you have like this the road, bouncy road like this, right? So if you go over this this particular bump, right? So this is so basically what are your system parameters here? So it's going to be dependent on the damper and the spring, right? So we just think of this practically, right? Just don't try to straight away go on and try to model this equation, try to get try to like get the free body diagram and do the modeling. Just try to understand this. So imagine like a shock capsule. So you don't see this in real life, right? You see something like this. You see the damper like this and the spring. So this is what you see in real life if I'm talking about a motor bicycle, right? So imagine you repair this bike. There's some sort of like a problem in the bicycle, and you repair it by yourself, and you replace the spring and the damper by yourself, but you don't like tend to make any you know, like you are not going to like look into the facts of the spring and damper. You just go and just purchase whatever the spring and damper that's available in the market and buy. And sometimes you might not get the perfect output, right? So sometimes say you go over a pothole and your bicycle goes, and if you plot if you take this particular point as a reference point, and if you check the displacement of this point with respect to time, it might go like this, right? So this system, what you say is like, so it means like once you pass this particular point, your bicycle will keep on bouncing like this for some time, right? Okay. So this is basically, let's say, whiting. Okay. And there are some occasions where where the damper is very strong. The damper is very strong and the spring is actually, the spring constant is very low, right? Then you will actually get a response like this. Right? And if these are optimum, you will get a response like this. So it's like, I will draw in the same plot so that you can understand. So if the conditions are optimum, you will get a response like this, right? So these are actually obtained based on the system poles, right? The system poles are dependent on these system parameters. The system parameters are simply, in this case, you can say this is ky t and this is by dot, right? So the system parameters are simply k and p. So this system is going to be entirely dependent on the spring constant and this thing, what do you call the damping coefficient, and obviously the mass, right? So what you can do is you can like so you want to get this type of response, right? So what we call this a critically damped system. Critically damped, right? This is an underdamped. This what you see here is an underdamped system, and this is an overdamped system, right? Okay, so so these are like some basics that you, I think, remember from I guess controls, right? So give me a second. Sorry. So so these actually, like, you all know, right? So this is something that you all already know. You all have studied this under control systems. You all have completed the module. So after that, you try to get this system, and after that you try to do some certain variations, right? You try to like change the system parameters by doing certain sort of adding some gains and stuff, right? You do it in under PID controlling, right? You try to add some gains to the inputs and try to like change the system, right? You try to get the feedback from the system, and then you try to get the feedback as an error and try to like modulate the signal that's going to the system by changing certain parameters, right? So you do all this under control systems, right? And then I'm not sure that you all have done this, but so you all have you all done discrete control systems yet? I don't think so, right? In the first module, you all did analog control systems, right? You all didn't do signal Nichols and all, right? Just analog. Yeah. So you do all these things in control systems, right? This is like what you all have done in that module that I explained. But so if you take the entire the vast spectrum of control theory. So to do all these things, you should like so under controls engineering, what you actually expect, is like to have like a broad understanding of all these elements, right? So if you have like an entire process, if you like want to say you're designing something like say like a complex control system, then if something goes wrong, we have to check, right? Where the system error is, where the issue is, how to troubleshoot. So that's basically the overall idea of control systems. But under modeling, so basically initially before you guys, this module was actually offered before the control systems module, right? So in control system, the overall objective is to like understand the big picture. But in this module, what we are doing is so to analyze any control system, you have to have a mathematical model, right? Without that, you can't work with that. Say you are going to like work with a plane, like a passenger aircraft, right? You can't just say you want to go and implement a PID controller there for flight controlling. So you can't just take a $1 million flight and just fly there and like say okay, we can modulate the gains here, and the response will be like this. And if you do that, the plane will crash, right? You can't say okay, now I want another plane to like check this out, right? You have to first try it out on paper, then on a simulator, and then implement that in a practical system. But to actually do that, we should have a model of that system, right? Either a computational or a theoretical model you should have, right? Or another example, right? Say you want to like develop a pulse, like what do you call the a pulse make, right? That's what you call it, right? Like I forgot the name. Yes, a pulse make, right? So a pulse keeper, it's something like a device that you plug it into your heart. So there are some people who have like varying oscillations in the heart, right? Varying sort of frequency to like keep that in a balance. So you call it palpitations, right? To control that, you like add something called a pulse maker. So so what happens is, right, not a pulse maker, you call it a pacemaker also, right? Pulse or pacemaker. So so what happens is, right, like you can't like go to the lab, develop a pacemaker or a pulse maker, and then just plug in a battery, put it inside the person's heart, and say, okay, now it's working. So if by any chance it doesn't work, then of course the person's going to die, right? So you have to have a model of the system. So to model this system, you should have like a fundamental understanding of how the system works, right? So for that reason only, you all have been taught all these lessons from since I think grade 7, 8. You are taught about basic governing laws in physics, right? You all know about the Newton's laws, right? The Newton's what do you call the dynamic laws? Then the Newton's the second law of Newton's, like the F equals ma relationship, and then the Kirchhoff's laws, the KCL, KVL laws. Then Maxwell's equation for magnetism. You all know this thermodynamics equations. Fluid dynamics relationships. All these things you all have been taught to understand the governing dynamics and the governing bodies of each of these systems, right? So what you do in modeling is you use all of these systems. You use all of the systems to like develop some sort of like a mathematical model on paper, right? So after that, you can use the model as some sort of like a plant that you can give certain inputs and see how the response is, right? So to make that easy, right? So you know that these models on paper, it could be like very hard to analyze, right? So if you take this system, right, this is second order model, right? This is second order model. And if you take like a basic system like a RC circuit, that's a first order model. You all know about first order models, second order models, right? So you have to like know now these models, those models actually occur in the time domain, right? So you can't analyze time domain equations because, I mean, you can analyze, but what you get in the time domain is a differential equation, right? So based on the order, it can be a first order differential equation with one derivative order, or a second order differential equation with a second derivative order. So these are like certain, so these physical or natural systems, once you model in paper, will have a mathematical relationship of that sort. So based on the differential equations format, you can call the system a second order model or a first order model. So there can be higher orders, right? There can be zeroth orders as well. We are not going to talk about that. Those are linear, plain linear systems, but there can be higher orders like third order, fourth order, fifth order, right? But usually what we do is we try to approximate all the higher orders to second order. So simply we can like sum up by saying we have second order and third order systems. So, sorry, first order and second order systems. So you all know that the general responses for these systems, right? You all have learned this, no? So what we try to do is we try to represent all the systems in this world in this particular format, right? So in this particular format. So there are certain formats like where we used to like model these systems. So one fundamental way of doing that is using the transfer function, right? So basically what you do is you have a time domain system, like say this one, the what do you call the spring mass damper system, right? So you have that system. So it actually accelerates, right? There's an ms double dot over here because this system accelerates, right? So it's an mx double dot here, right? So if there's an mx double dot over here, this system is first order, right? This is second order, right? Because there's a x double dot here, right? So we have a second order system. That means we will have what? We will have a differential equation of the second order. So we don't like to solve second order models, right? We don't actually like, we don't actually like to solve differential equations in a time domain. So what we do, we actually convert the particular model into the S domain or the frequency domain. So what we do, we use a tool called Laplace. We convert the second order system into the S domain, and we have an algebraic format, right? We don't have these derivatives and all this, right? So if you have like a sort of like a complicated differential equation, you can simply write it as like an algebraic format. So as an example, let's say this is like a recap that I'm doing, right? Say we have something like say a2 t2 yt t2 squared plus a1 dyt dt plus a0 yt, okay? It's equal to say xt. So once you get the Laplacian, what you will get? You will get a2 squared ys plus a1 ys plus a1 sys, right? a0 ys equals xs. And you can solve this and you can get an equation in the format of hs squared hs equals k omega squared plus 2. This is actually a theta omega ns plus omega n square, right? So this is the second order model. Right? So you can see this, we don't have this complex derivatives, second order and first order differentials inside our system, right? We have like a polynomial sort of equation, right? So these actually correspond to certain elements, right? So K is actually, you can call it static sensitivity. In some areas, I think you all call it something like something else, or you can call it the steady state, all right, or something. So if it's a sensor, you call it static sensitivity. Or if it's like a overall system, you can call it the steady state, right? So you all know the steady state and transient, right? So if you have a system, if it like takes some time to settle, so this is like the K. This is like the this is like where, like, say the motor bicycle, it bounces off and settles on one point, right? You call this the steady state, right? K. And the moment, the time it takes to reach that, this is the transient, right? This particular phase, transient. And so there's something called the time constant. The time constant actually corresponds to like a particular period of time. So the time, basically time constant is defined as the time taken for this particular system to reach 63.2% of its steady state. So simply by the time it reaches around 5 to the time constant, it reaches like 99.9%, right? So these are some things. So there are also other factors like theta corresponds to the damping coefficient, and then omega n squared over here corresponds to the natural frequency. Omega squared corresponds to like so that is natural undamped frequency, and this is the damped frequency, right? So I think you all know these things from control systems. I don't want to touch these again. You all have, I think, done this like to like a high extent in control systems. So this is what actually we do with this in this module. So we actually try to go to the in-depth forms of like modeling a system. So this is actually a transfer function representation, right? This HS is actually, so it's simply HS simply means, so you have like an input, say input is in this case, let's take the input is like as XS. So it's simply a output of input, right? So so I can't remember what I took as the input here. So Y is actually the output, right? So it's like, say Y is so XS, right? So any of that, I mean, simply that's what you get as a transfer function. And if this is like mostly for static systems, and if you have like a very dynamic system, then you use some other methods like the state space representation, which I think you will be doing in the lecture, right? The state space representation. And then you will be discussing about some other methods like linear graphs and all, right? So basically you will be like taking this particular, like if you take control systems, overall control systems, you will take one particular element, that is modeling, and you will go this writing pad is, you will be analyzing this particular part quite extensive. Okay, that is what you do in this module. And if I talk about the labs, right? So I think you all have done this what do you call this Simulink up to some extent, right? You all have some basic understanding of Simulink, which I will not be covering once again in the labs. I think you have done this under systems engineering and control systems both. So I expect you all have that knowledge, because if we are going to do those things once again, it's like going to be a repetition, right? So if by any chance you all can't remember any of those, you can revisit the labs. I think for systems engineering, Simulink was covered by Mr. Amidu. And for control systems, I think Mr. Bevanta covered the lab. So I think you have like some background in Simulink, right? So any questions up to this point under like the overall the big picture of the module? Big picture. I'm actually focusing on the practical aspects because I'm in the labs. So in the lectures, I think you all will get a much comprehensive idea of all these things that discussed. So that's why I actually rushed through this. So if you can't remember any of these, doesn't matter, right? These are like simply what you all have been already doing in control systems, right? So modeling in control systems, right? The modeling part in control systems. So this is like the same thing that we'll be doing in this module, but up to some sort of like a higher depth, right? We'll be trying to reach a little bit deeper in the modeling aspect. And so Simulink is one software that I'll be using. The other software that I'll be using is MSc Adams, right? So MSc Adams is simply like, it's like this now. In MATLAB, what we actually do is we do some sort of like a computational modeling, right? We actually do some sort of like a computational modeling. We try to like get a system, a mathematical representation, and you try to like look at that in a mathematical way, right? So that's what you try to do in MATLAB. But if you look at it in a dynamic manner, right? If you try to like look at the entire system in a much more dynamic way, then you have to like think about certain factors like you know how different objects work, operate under certain forces and all these things, and you call this multi-body dynamics or multi-body physics, right? So as an example, say something like a manipulator, like a robot or something. So in that case, actually what you actually do is you have multiple links with masses, and which show different dynamic and kinetic and kinematic properties, right? So kinetics, you know, difference between kinetics and kinematics, right? So kinematics means like the dynamic relationships between links, and kinetic means like overall it's like the big picture. Say you are throwing a ball at some, you are playing cricket and you're bowling at the batsman. The motions, like the forces acting on the ball, is dynamics, right? You have an external force and you have like a certain drag forces from the air and all these. And say you are like walking and you try to like look at the forces acting on your joints of your knees and your body. So these are kinematics, right? So that's the difference between kinetics and kinematics. So I think you all have done dynamics and mechanics of machines in the first year and second year. So these these forces, right? The kinetic and kinematic forces can be actually physically observed in MSc Adams, right? It's like a very high-powered multi-body dynamic software. Okay, so these two softwares we'll be using. We'll just be having a low number of labs. Actually, we'll just be having 5 labs at maximum. So simply there will be two labs from MATLAB and 3 from Adams. That's the plan. So it might vary, right? Because Adams is not a very user-friendly software. Some people obviously might be might have some issues when you're installing Adams. So I will upload the guide for Adams how to install Adams by this week. So don't wait until we start the labs, right? Because I think we have to finish off all the labs within the next 5 or 6 weeks, right? I think there's some requirement like that. So don't wait until the last moment. Finish installing the lab software, okay? And if by any chance, if you have any issues with installing software, let me know. So we'll try to figure out something if there's such issues, right? So, okay. So any questions up to this point? Any questions? So you all are familiar with the overall modeling aspect, right? No questions, no issues there. I mean, the basics of system modeling. Okay, so by any chance, if you all are not familiar, so you can go through the lectures and also your third year, first semester modules, right? Control systems and control systems. And for Simulink, you can go through the early labs if you're not familiar with the software. Okay. Okay, so no questions, right? So either you all understand everything very well. If not, you all don't understand anything. So I'll assume that you all get it. Okay. Okay, so we'll look at simple models first. So like a small recap of how to like model a basic system before we go on to the lab. So if I look at the lab here, so this you all have done, right? So I'm not going to waste time on this, but before we go to the quarter car model, we'll have to see how this is, because once you understand this, of course, it's very easy to understand the quarter car. Because I have seen fourth year students now, so I'm involved in one of these final year research projects in the final year. So one student actually asked me like how to draw the free body diagram of a system. Now, free body diagram actually you start drawing in A levels, right? In A level physics, I think you start drawing free body diagrams, and in under applied mathematics course you draw free body diagrams. Okay. So this actually you should know. Okay. Free body diagram modeling is something that you should know. So it's like if we just consider this spring mass damper system as an example, okay? And by the if there's any particular notation that has been used by sir in the lectures, you can use those. So just try to capture the idea, right? Don't memorize these things. You can't memorize it, honestly, right? So you practice for something like this and go, okay? You practice for a system like this and go. And you just practice it for a system like this and go. And for the exam, you get a system like this. Say the same here. This thing here. Say, let's say without the spring, you have a damper here. Let's assume. Right? So you have some sort of like a pulley sort of thing. So you have force here. Right? So, and here you now say there's a friction coefficient here, right, of mu. Now when you are given something like this, you struggle, right? That is because you actually don't understand the overall idea of what you're doing, right? So it's better if you understand what the entire process of doing a problem like this, right? So so simply if you take a mass here of M, and if you apply a force, say, before that we'll model the system, right? If you have mass of this, and so it's simply like another shock absorber, right? So something like this. Okay. So first of all, you have to consider a reference point, right? If you get a system, you should have like a reference point. So in this case, I will consider this particular point as my reference point and the displacement as yt. So you may use xt or whatever you want. So whatever, yeah, okay. So yt. So then we will have like a force applied over here. Say so there's a motor bicycle, a person hops in, right? So that's the force. So a person jumps on the bike, right? Like a static, like non-moving bike. So we can assume to be say the mass of the seat, right? Or in another case, if the bike is moving, you can say that like there is the M accounts to the like the weight of the motor bicycle and plus the weight of the mass of the person. So the force is something that's given by the ground because of this bump or something. Sounds like an impulsive force, right? Or say like a unit step. So this is like the overall system. Okay. So there's a spring. The spring actually resists displacement, right? So if you have a spring like this, and if you try to squeeze this, right, you are trying to displace the spring by some way, and the spring resists that displacement, right? So by a factor of k, we call this a spring constant, right? So since this resists the displacement, we can write this as ky. It's a function of time, right? I'll just write ky for the time being, if not. Okay. And if the force is acting this way and the displacement is going to occur in this way, then it's going to resist this, right? Yeah, upwards. And the damper is going to resist velocity, right? If you take a damper and try to slowly press that, it's going to go in that same speed, right? It's going to go inside. But if you try to increase the velocity and try to push it hard, then of course, then it's going to resist that, right? So it's going to resist velocity y dot by a factor of its damping coefficient, right? So this is the system, right? So we can apply F equals ma, and we'll get my double dot is equal to the variance of the forces, right? So so simply this is F equal, this is the ma part, right? So the F parts is the difference of the, it's like the resultant force, right? So you have the external force minus the resistive forces. Okay, you get the idea, right? So now we have to like isolate our highest order by this y double dot. So we'll isolate this by sorry, we have to isolate the external force, right? So what we can do is we can isolate our ft, which is this, that is equal to m. So m. So basically, we had to anyway we had to make the coefficient of highest order 1, right? So anyway, I'll do it at this particular point itself, right? So we have to divide everything by m, right? So this becomes 1 over m. This becomes k over m plus minus b over m. So this becomes so if I isolate the external force, f 1 over f becomes y double dot t plus k over m k over m yt that's it, right? Sorry, I missed this thing, the damping factor. So it's going to be a b over m. This becomes positive because I take it here. B over m y dot t plus k over m. This writing pad is like sort of having some issues, so just ignore if. Yeah, okay. So this is the overall system, right? So you can see that this is second order system. And after that, what can you do after you get this response? So this is second order model. Then what you can do is you can take the Laplace transform of this particular equation using the Laplace table, and then you can actually model the system, right? But for this particular case, this response obtained up to this point is okay. You want me to like model a electrical system also or not? Or are you all like familiar with electrical systems? You don't have to. You don't want me to do that, or do you want me to? Okay, so comfortable with electrical systems, right? So I'm not going to model an electrical system then. So simply, this is like how you like draw the free body diagram. So simply, I mean, in this case, I didn't like draw the FBD, but if you want, you can like take this out and draw the free body diagrams, right? So there's going to be a force here. Okay. Okay, so right, so you can draw this, but yeah, or you can just directly get this up, right? And you can get the overall acceleration as my double y. It's equals to y my double, right? It's ma. Okay. Okay, so that's it. Now let's go to the Kotakama, right? So I go to the lab that you all have to try. So the only difference here is that there's another mass downwards, right? There's another mass downwards, which actually sort of like, that's another sort of like a part, because we actually don't consider the tire over here. That's what happens. So we, in the spring mass damper system, what we do is we consider only up to this point. We are completely ignoring this, the wheel, right? So now this particular spring is like a sprung mass, right? So this spring sort of like sprungs this mass. Okay. So now what happens is, like, say this the wheel actually has this tire stiffness, which also accounts to some sort of like a spring effect. Okay, if you take a wheel and if you like throw it out of say like say if you count to slit with a car wheel and throw it out of the fourth floor window, it will bounce, right? So the bouncing is caused because of the stiffness. So it has like some sort of like a elastic potential inside it. This elastic potential actually causes the spring to bounce. Okay, so the tire to bounce. So this actually accounts to like the vehicle as well. So imagine like we consider only this part, and we get a, so you tune your system, your second order system, to critically damped This is right, but in reality, once you go to implement this, no, you don't account with this, right? You don't account with this, and suddenly your system becomes acting like this. That is because you see this, you don't account this tire stiffness, right? So say now we'll talk about say like underdamped system, right? You model the system and you have an underdamped system. So I just want to understand whether you all have obtained the idea of this overall modeling. So let's say an underdamped system. Okay. So can someone tell me here? So you actually, like, say you are a vehicle, an analyst, right? You're like a person who models the vehicle's characteristics, and you get something like this. You check the damping coefficient for a second order model, and you get the damping coefficient between these points. Okay, you get this between 0 and 1, and the response you obtain is somewhat similar to this. What do you think you should do? What's lacking here? What's lacking here? I'll ask someone. Okay, I will ask. Okay, I'll ask Vijay. So, what do you think? What's we have to like fix the system? What would you do as an engineer over there? Vijay Ratna, MPR. Okay, Samarakon. what would you do like if you like get a response like this? So this is like the system this is a system parameter, like so this is dependent on so you know the zeros and I mean the poles of the system, right? It's going to fall it depends on the system parameters, simply the spring coefficient and the damping factor, right? What are you going to do? Okay, I will ask Gunawardhan.
So you increase the damping coefficient?
Yeah, correct. So that's actually the understanding you should have, right? So if you get a system like this, a response like this, that means it's like it's sort of like under damped, right? The name itself suggests that. So it's like the spring is like the spring constant. Either you should have to like reduce the spring constant, or like you have to increase the damping coefficient, right? So simply what we call a critically damped system is when this is equal to 1. So when this is equal to 1, what happens is this is actually like corresponding to like in a second order system, it's corresponding to like the coefficient of the highest order system divided by the first order function divided by 2 into the power square root highest order into lowest order. You can like, go through those notes, but in this sort of case, what happens is the poles are actually say it's like in the sort of like in the the real axis. I mean the real axis, but there's 2. But you want like try to make these poles coincident, right? So that you have only one equal pole. So that's when you get this. You call this a critically damped system, right? So when you're actually trying to get this, if you don't account this unsprung mass and this the stiffness over here, that could cause issues, right? So you can like simply draw the. So this is the lab task you all have to do for the lab. So I'm not going to like go into that in depth, but simply I'll explain. So you can take this MS mass separately, right? So this mass you can take separately, and so what are the forces acting on this mass? So you know that there's going to be, if you assume that like the X3 is going to be this direction, right? So we assume now we are considering an occasion where the forces are given by the springs, right? But the overall force, let's assume that it's acting on this direction. So we have ms times the acceleration of field. So the direction actually doesn't matter. If you are assuming the direction wrong, it will actually come as a negative value. So this is the force, right? So we have the displacement here, that is x3. So the x3 displacement actually will have an acceleration, a velocity later on, and an acceleration, right? Both in this direction. So the corresponding force, that's the resistance given by the spring, right, can be taken into account. So we'll consider this particular occasion where the displacement is happening in this way, and the spring is trying to hold this mass back, right? So so this is K spring. This is the sprung spring coefficient, and the overall displacement we can get as x3 minus x2. Okay. So, and there's going to be like a resistance for the velocity also. So now the picture is happening. Okay. So the mass tries to go up because the displacement is going to happen upwards, and the spring and this particular mass actually, which is on top, is still acting downwards, but it's like an occasion like this. Yeah, like the overall system goes up. So we are considering this as like an interval like this, right? So, so there's a resistance given by the damper like this. Okay. So these are actually, this is the free body diagram of this part, right? So if you consider the unsprung mass, right? So unsprung mass is mu. Okay. Now, obviously, these forces are going to act on this, right? So since these forces are acting on this at these points, there's going to be resultant forces equal to this. So for like convenience, I will name this as say K. I will just rename this as if case, this as FB. Okay. So this is F case and this is FB. And there's a force of this particular mass acting downwards. In this particular case, since we assume the external force is acting on this, we will assume force is acting here. Mu. So what's the displacement? We just assume it's x. Since this is x2, the reference point, we'll take this as x2 double. So here the displacements are occurring with respect to this point upwards, that is x2. So there will be variations of x2, x2 dot, and x2 double dot. Okay. These are three forces. This is like a displacement, and these are not forces actually. These are different types of dynamics. Okay. And there's, apart from that, there's another force caused by the stiffness. So we are considering an occasion where the displacement is upwards, and the stiffness or the unsprung spring is actually holding this back, right? It's trying to go up and it's holding it back. So we'll just consider that force. So it should be actually act on this particular axis, but since that's going to be a little bit confusing, I just right here. This is actually wrong. Okay, you can't have if you like consider this like this force has to be co-linear with that, right? Because you know the resultant of these two forces is going to be here, right? Somewhere around here. So and this force, so the resultant of the forces downwards should be co-linear with the forces upwards, right? For a balanced system. But just for simplicity purposes, if not, you'll be confused if I draw this here. So I will just draw this thing, this tire stiffness force as KT into what happens here. There's a displacement of x2 minus x1. Okay. So because the overall displacement, this this part goes up by this amount, but at the same time, this part goes up by this amount. So we have to get the reduction of that, right? Similar to here. So this part goes up by x2, this part goes up by x3, but the effective displacement is x3 minus x2. Okay, so these are the free body diagrams. Okay, now you simply have to apply F equals ma to this, right? So you simply have to apply F equals ma to this. So if you apply it to this particular part, you will obtain. So I will assume this MSX3, right? MS3 double dot is equals to. So these forces, now these are the forces. So we can assume these are acting opposite to the direction of this particular force. So, I mean, you can assume the other way around as well, right? Doesn't matter. Case, unless they have specifically mentioned. So in this case, we'll assume, I mean, x3 minus x2 minus bs x3 dot minus x2 dot. Okay, so I simply just got the force differences. This force, there's no external force acting here, but there's this this one. Okay, and for this particular part, this is the equation 1. For 2, we'll get the similar one. So you have to actually substitute these particular values here, but I will just write I will use the same format. mu x2 double dot equals f ks plus b minus kt. Okay, so you can use these equations separate. So this is like the overall model. Okay, you have to model. Let's try the workings out. Okay, so there might be some errors, just plus minuses, just check them. I don't think any errors are there, but yeah. So this is, I think, the first part of the lab anyway. Just have to model this. Yeah, just draw the free body diagram and get the differential governing equations, right? And the system model, linear, non-linear. Is the system linear, non-linear? Can someone answer? You all have modeled the quarter car in the lectures, right? So is the system linear or non-linear? Sorry, I didn't hear you.
It's linear.
Yeah, why? Why is it linear? So we are actually seeing a translational motion, right? Right, we are seeing a translation motion here, but you have to justify. I mean, now I'm not going to explain this. You have to go through and write a brief, like a small reason why, but it has to be correct. Okay, let's go through because I want you all to go through the lecture, but the response is correct. So simply now the two parts are done. Now we'll go to Simulink, right? Simulink model you have to develop based on this particular set of equations that you obtain. Okay, so I will go to Simulink sorry, the MATLAB. I'll open Simulink here. And I have actually simulated this earlier, modeled this earlier so that you can like refer, but I'm not going to share this with you. You have to model this by yourself. So if lab 2 So this is like the simple model for like this system, right? So we are having 3 velocities. So x3, actually we can like so you all have done simply it's like now don't refer to this and build the same thing. Okay, this is going to be pointless. So this is like this simple. So I just want to show you the response of this. Okay, so we'll go to the MATLAB code. So simply yeah, you can like once you have to get the equation. So based on the type of equations that you get, your model is going to be different. Okay, so this model might not be the same that you get. So so these gains actually correspond to this actually corresponds to the sprung paths, damping factor, the sprung spring coefficient, and the unsprung spring coefficient, right? And here this is actually corresponding to the this part actually corresponds to mainly the unstrung part or the tire part. Okay, and this part corresponds to the sprung part, right? So simply it's like the first half, the second half. So you can see how this is obtained. So this is the main mass, right? MS, or like the main mass. So these forces I have commented here, the input that is coming here, the overall input, right? So this is the spring coefficient of the sprung part plus the displacement difference plus the what you call the damping coefficient plus the velocity differences. So that comes here. So here you get simply you get 1 over ms. The gain of 1 over ms is given to this part, because we have to, like, if you look at the equation, you have to you get mu x2 double dot, right? So to isolate x2 double dot, you have to divide everything by 1 over ms, right? Sorry, you have to divide everything by ms. So you get something like this. Then you get xt double dot. Then if you want to get so this is the acceleration. If you want to get the velocity, you have to integrate it, and you get xt dot. The displacement, once again you integrate it, and you get xt, right? And here you can observe the displacement of the sprung mass, right? Because if you look at the lab sheet, here, right? Xt is the displacement of the sprung mass, right? You can observe the displacement of the sprung mass, and you can observe the displacement of the unsprung mass as well. That is x2, right? It's x2. So similar method do this, right? And we are giving the step inputs here. So if I simulate this, I have to run the code. So the parameters given are these. So these are given in the lab sheet. This is the mass of the sprung part, unsprung mass, or the wheel, actually for the wheel, okay. Spring constant, tire stiffness, the shock absorber. This is actually we can call the damping coefficient, right? So damping, I think the lab sheet you have been given as that, right? So I'll just keep it at that way. Shock absorber constant. So you can change these values and see how the response is. Okay. So I will just run this and I will. So if I go here and run this as well, you can see the response here. So we check, first look at the wheel response. Okay. So there's like a high peak suddenly. It's like an impulse and it settles. Okay. The displacement goes to a high peak and settles. So you can observe this response of the overall system. So there's an overshoot, high overshoot, and then it's undershoot, and then settles. So you can see the unstable duration is close to 2 seconds, right? Which is not that bad, but you can try to optimize the system. Okay, you can try to optimize this overall by changing certain values. So we can say increase the spring constant, like the sprung constant. We can like say we make it like 15,000. You can increase that to 15,000, and we can then see what happens. Okay. Then we'll simulate this and see. This the sprung part was introduced, right? So the wheelbase, you can see not much change, but here you can see that the amplitude of the oscillation has increased, right? So you can like modulate and see what happens. So you can say increase the damping factor, say 6,000. You can observe this. So this is slight deviation, but the displacement is going to still be somewhat the same. Okay. So you can like develop something like this. And if you want, you can like, it's preferred to like model something, a system in this particular format. So I will show, because if you go to like say these function blocks, it's much easier to understand this, right? So we have the step inputs sort of like superimposed here, and then added here as the x1 input, right? So this is like the displacement, initial displacement from x1, and this is suspension part in the car part. Okay, so I will load the code for this. I use separate variables here, so it's not easy to like. So once again, I used here prompt. So you can see the suspension basically means. So you can see that there's like the overshoot is somewhat lower than what we obtained earlier. It was 0.05 earlier, so it's somewhat lower than that. And for the car, you can see that there's like a little bit of if you look at the transient, it goes for more than 2 seconds, right? The early system it had just 2 seconds, it settled, but here you can see that it goes a little bit more than settled. So it's like a sort of like you can say sort of like an underdamped system. Okay, so you can, I'm not sure the lab sheet you have been asked to like check the optimum system, but you can try out certain things, right? So this here we have 60,000. I will just try to reduce this to like say 25. 1000 and increase the damping coefficient to say 1000, and we'll see the response. Right. So now you can see that the transient has reduced, right? Transient has reduced and the system stabilizes by 2 seconds, right? Early it was, but you can see that there's a high impulse, right? The amplitude of the signal, but it's still not up to the point that it had earlier, right? So the system is a bit more optimized now. So earlier I think it was above 0.035, right? It was between 0.035 and 0.04. So it's like a more smoother system, this. So you can try out certain things, right? So simply it's like a practical scenario. You can actually, so based on this, you can simulate this and you can tell the manufacturer, okay, I want my spring to be this value. The spring constant has to be this value. And the damping coefficient has to be this value, right? And so by any chance, if the mass is going to increase, say 1000, then you have to then, of course, so the maximum mass that the system is capable of having is 1000. Then you have to run and see once again. Okay, so transient still goes a little bit over 2, but still that is okay. As an undershoot over here. But still it's fine, right? So it's fine. So you can like modulate your system like this and like give the manufacturer and say, okay, these are the parameters I want. This is the overall I mean, we do all this for a reason, right? We just don't want to like observe the response and be happy about that. There should be a purpose in the like a actual reason for us to do all this. So the ultimate goal is to find the optimum conditions that that are controllable in our side, right? We can't control the road conditions, right? We can't control the road conditions. We can't control the mass of the person who's going to jump in. We can limit that, right? We can say, okay, this vehicle is going to sustain only 1000 kgs or 700 kgs, that we can specify. But sorry, I mean, not the person. I mean, the overall load of the vehicle the vehicle should be 700. So we can limit the passengers to say 5. So if a passenger weighs an average of 100 maximum of 100 kilograms, if we can estimate all the passengers to be of 100 kgs, and we can say, okay, if there's 5 passengers going in the vehicle, that accounts to 500 kgs plus the weight of the chassis and the other components, the engine and all. We can specify the mass of the sprung mass, and the wheel base also we can calculate the mass, right? So these things that we can get from the manufacturer, but our interest is in these factors, right? The controllable factors, I would say, are these. This, the spring coefficient, and these two, right? This also, now the unsprung stiffness or the tire stiffness is also some sort of controllable, but I wouldn't say that's exactly controllable, because we can't. So if you are like manufacturer, you get like ready-made tires, right? So you can't actually control this. So these, but by controlling only these 2 factors, you can actually optimize the system, and you can say, okay, these are the features that we want for the vehicle to have to obtain this particular response, right? So so this is the overall objective of what we are doing, right? So this is the lab task. So actually I have actually, I mean, you have to do this by yourself, right? You have to attempt the lab by yourself. So don't just rely on whatever we did in the lab, right? Try to do it by yourself. That's how you learn. Okay. Try to attempt it by yourself and without any help. Okay. And our theory, of course, you can go back and like refer to whatever you have done in the earlier years. But it's better if you actually do the modeling part by yourself. That's how you understand the overall system, right? The system modeling aspect. And also try to understand, as I mentioned earlier, try to understand why, like how this is done, without just mechanical doing it. Okay. The intuition behind all this, you have to know how this is like, how to approach a problem, the understanding, the fundamental understanding of the concepts you should have, right? So then it's of course easier for you to like approach a problem that is completely novel, right? And in this module, try to see the parallels between mechanical systems, electrical systems, fluid and thermal systems, right? So almost all these things are quite similar in nature, right? The application would be different. The application would be different, and the overall system would be different, but the response and how it actually works would be quite similar in nature, right? So you can like observe how these certain characteristics are parallel with each other. As an example, if you take a fluid accumulator, it's like the same response like a capacitor, right? So you when you model the system, whether it's a fluid system or whether it's an electrical system, the capacitor and that you model similarly. And what's the say the governing equation of the inductor? So the inductor voltage V is given by L di over dt. So the rate of change of current times the inductance, right? Use whatever the the voltage change, right? So it's similar to the dampers model, right? So it's quite like something like that. Okay. So I'm not going to do the electrical modeling because you all are okay with that, right? So but try to understand the basic concepts of that, right? So when you have like something like an LC filter, right? You all know what LC filter is, right? Or like say if you have like a system like this, like so let's take something like a buck converter, right? So you have like a say you have a switching gate over here, right? So usually this is not something that we use. We use something like a MOSFET, right? So so we have a gate voltage here, and usually we have a diode door here. I'm drawing this by memory, okay? Just correct me if I'm wrong. Okay. So simply I would have like say an inductor here, and we have a parallel capacitor. Have you done power electronics? Have you done power electronics? You have, right? Yeah, okay. So you all know this. So you have the load over here. So this particular part we call, I think you all remember, you call this particular part the LC filter. LC filter, right? LC filter. So, so if you take this part, so why do we call this LC filter? Can someone explain why we call this the LC filter from your electronics knowledge? Now I don't want to go, deviate out of the topic. So simply what are we going to do? We are going to give like a pulse here, right? We are going to give pulse input to the MOSFET, right? That's going to like create like a duty cycle, something like a PWM. And we are going to get an input of, say, we are going to give 12 volts here. We are going to give 12 volts input here. We want 5 volts output here. And similarly, you are not going to get an output like this. As soon as you want it, you are not going to get the 12 volts input, 5 volts output. There's going to be a transient, right? There's going to be noise. There's going to be a ripple, right? You give a 12 volt input, the output is going to look like this. Similar, I will just something like this. This might be 5 volts. So we have to account to the transient and we have to account this ripple as well. So there's a ripple here. So this ripple is actually, now you all know a capacitor in a DC circuit is an open circuit, right? A capacitor in a DC circuit, there's no a current doesn't conduct through a capacitor in a DC when there's a supply of DC, right? Then why do we have the capacitor over here? What's the reason? The reason is, so you all know the how these work, right? The inductor, so there's going to be, so in the switching mode, say when Q is on, so we have the T on mode, this is the on mode and the off. In the on mode, current will go through this, the diode will not conduct. And if you take the positive and indicate the polarities, it's going to be positive, negative. There's no current through this. The load resistor, there's going to be current like that. We can apply Kirchhoff's voltage law and KCL at this particular node and find the values. You can find the inductor current. This is IL. And you can find, you can simply find the inductor current. The inductor current will be going through this thing. But as soon as you remove this during the off state, what will the inductor do? The inductor, you know from the Lenz theory, that whenever you have applied a magnetic force, voltage and applied like polarity somewhere, as soon as you remove that, it's going to induce another opposite polarity to rectify that. And that will actually cause, I will use another color. That will actually cause, now the capacitor will, release whatever energy stored there by itself, right? By itself, like this. So even during the off cycle, there will be the current continuation happening. But this will actually lead to like a loss of power. That's what happens, right? So what happens here is, so this LC filter does is, the DC part will go through the load resistor, but the AC ripple like this, the ripple part, right? So you know from Fourier series, if there's a signal, the signal has a DC component plus a collection of what you call harmonic oscillations, right? Or if you can say A sin omega t or cos t. This AC part will go through this capacitor. So we'll be able to remove this ripple through the capacitor, and we'll be able to supply this DC potential, DC current through the resistor. This is the overall objective of using the LC, this thing, right? So if you model this system, you will once again get a second. If it's like a RLC circuit like this, you will get a second order, and if it's an RC circuit, you will get a first order, right? So once again, you can get the transfer function, model this, simulate it, and find out. So for what particular inductance and capacitance you get the most optimum system, where the transient is low, the switching is actually here in this case there are different governing factors, like the switching frequency matters. I think you all know about this. Switching frequency matters, and all those things come into account. But you can actually simulate and find out the optimum conditions for this circuit to function, right? Okay, so this is like a small. I'm not going to do the modeling because you are familiar. But I hope you all are clear with try to find the parallels of these systems, right? So it's much more easier for you to understand the overall objective of this particular module and all this, right? But we will not be going into electrical systems in detail. It will be mostly mechanical. But if you all want to for additional knowledge to know about electrical systems, let me know. I will do an extra session on the electrical systems. Okay? Of course, with the sir's permission, right? So I think that's okay for today. If you all have any questions, you can ask. And if you all have any doubts, please contact me through mail, right? I really have bad tendency to check messages in WhatsApp. I really miss a lot of messages, most important ones as well. So it's better if you contact me through mail. Okay. So so the submission for this particular lab, I will say you 1 week, right? 1 week I will give you for this. So for the lab, the delivery, I think we can complete all the labs within 4 weeks, right? So this lab we'll have today. Next week we'll have another lab for MATLAB. Next week, I think most probably we'll have some sort of like a assessment for you all. It's like an assignment. So for that lab, I will just give you sort of like a basic introduction. So it will be, I think, the last Simulink based assessment that you will have. So it's going to be something that you will have to use your knowledge and do. So that will be given some time, right? We'll have the session next week, but you will be given the entire semester, I think, for at least 4 weeks to complete. And we will start the Adams labs the week after. And Adams labs also we will be able to conduct some labs pretty soon, because it's like a basic software. So that will be the delivery plan, right? But apart from that, if you have any doubts to clarify your, discuss about, you can contact me via mail, or if you can meet me if I'm asleep, right? I'm not sure whether I'll be coming every day because of the crisis situation, but I'll be here on, I think I'll be here on Mondays, most probably Mondays and Fridays, I guess. Depends, right? You can contact, I can contact and ask if you have any doubts to rectify. Okay. So yeah, so I think that is clear, right? So well then we can stop the session for today. So we'll any questions? Is it clear for you? Whatever we did today, was it clear? So